Okay, let's get started. So I think today we'll be able to finish this unit on PCA. So last time we talked about what PCA is. The idea is that you have these feature vectors xi. You want to compress them in the sense of representing them approximately with some other feature vectors, which we'll call zi, that have a lot fewer elements in them. So the original ones have d elements. These new ones have capital R elements. And the way you do that for PCA is linearly. So you build a dictionary of vectors that are scaled and combined by multiplication with zi, and that gives you your approximate xi. So the smaller that you make R, the shorter zi is, the fewer columns B has. And the way that we design both B and zi is we want that their product, which is our approximation of xi, is closest to xi in the sense of RSS. So we want the sum squared difference between these to be small on average over our data set. So that's kind of what we're trying to do. Any questions on this? Okay, and then we went through, so the solution is that you first compute the sample covariance matrix from these feature vectors. We assume that they're centered, so we don't subtract the mean here. And then you do an eigen decomposition of them, which you can write this way. You look at the largest eigenvalues, the largest R of them. You then take the corresponding R versions of V, the eigenvectors, you stack them in a matrix, call it VR, and that is the optimal dictionary matrix. And then second, to make these approximation coefficients, you just take the original feature and you multiply it by the transpose of that matrix, and you get these original coefficients. And essentially, what we're doing can be illustrated this way. Let's say we start with three-dimensional feature vectors that live in this three-dimensional space. They are the dots. And here we say we want to approximate them with two-dimensional vectors. So we learn a two-dimensional basis, which basically gives us this plane. And so now our approximations will live in that plane. And in particular, for each of the original feature vectors, we are finding, so the approximation is the closest point in the plane. And the plane was selected so that the approximation errors, which are those lines, are smallest in RSS. So that's if you want to reduce the three-dimensional features to 2 dimensions. If instead you wanted to reduce them to 1 dimension, then you're looking for a line in this feature space, in the overall feature space, such that that line is closest to all your 3-dimensional samples in RSS. So in that case, the B matrix is just going to be a 1-column matrix, and the column tells you the orientation of that line. In either case, the Z coefficients tell you where you are along here. So for this case, ZIs would be scalars, and they would just tell you where along this line you are. In this case, the ZIs would be 2-dimensional quantities, and they would tell you where in this plane you are for each point. Okay, so that's the method. Any questions? Okay, so we went through this long proof of this, got to the end of it, and then we also talked about how you select R, the rank of the approximation. And we said rather than using RSS, or R squared, which is what we used for linear regression, we use something really similar called proportion of variance. And in this case, when you study proportion of variance, essentially what you find is that this is the ratio of the sum of the eigenvalues that we use for our approximation over the sum of all the eigenvalues. So as R gets closer and closer to D, this ratio gets closer to 1. We want to choose R such that this is close enough to 1 so that we feel like we have a pretty decent approximation. So we'll show an example of that later today. Okay, so today what we're going to talk about are some computational things. How do we do this in practice? And then we'll go through an example, a lot of visualizations. Okay, so earlier we said that this is how we start. We make this covariance matrix, we do an eigendecomposition. Well, it turns out that if you have a lot of features, just making this matrix itself could be computationally difficult. So there's sort of a shortcut that avoids ever having to make this matrix. And that shortcut is something called the singular value decomposition. So this SVD, how many of you guys have heard of the SVD? Okay, it's probably the most useful decomposition of all of them in linear algebra. So I want to talk about it just more generally. And one of the reasons why it's very useful is that you can apply the SVD to any matrix. So there's a lot of decompositions in linear algebra, like the eigendecomposition, which doesn't work for all matrices. Or, yeah, all of them have these restrictions. Well, the SVD works with everything. Essentially, what the SVD does to any matrix is it writes it as a product of three matrices. The ones on the outside are orthogonal matrices, and the one on the inside is a diagonal matrix. And one way to think about this, if you think about the matrix as an operator, as something where you take a vector, call it A, multiply it by the matrix X to get another vector, you can think of X as operating on A. And so another way to think about that operation according to the SVD is it's a series of three operations. First, multiplication by an orthogonal matrix. Well, it turns out that that is just a rotation. So rotation, scaling the individual elements, followed by another rotation. So any linear transform can be thought of rotate, scale, and rotate again. That's what the SVD tells us. And sometimes breaking it up this way can be super convenient to prove things or to understand what's happening. Okay, so there's actually two versions of the SVD. There's the standard one, and then there's this economy one, which has a lower computation, where you don't compute as many things. So for the standard SVD, like I mentioned, it's orthogonal, diagonal, orthogonal. So this U is an orthogonal matrix that's n by n. So up here, we're going to start by saying X is n by D. Okay, so n by D. Okay, so clearly the left dimension of U must match the left dimension of X, so U is going to be n by n. We said it's orthogonal, so it needs to be square. As we saw before, orthogonal means all the columns are orthogonal to each other, they all have unit norm, and all the rows are orthogonal to each other, they all have unit norm. And so what we saw today is, okay, you can also think about that matrix as a rotation. It rotates vectors. It never scales, it never changes the norm of vector that it operates on. Okay, V is also a rotation matrix. Now, of course, V being on the right side, V must match this dimension of D. So V is a D by D orthogonal matrix. And then what's in the center, S, is, we said, a diagonal matrix. Now, this is not necessarily going to be square. What we find for this SVD is that X and S have the same size, same dimensions. Or maybe I'll say the same shape. So let me make an illustration of this. So, for example, if X was a tall matrix, it would look like U S V, or V transpose. So the key point is that this shape and this shape are the same. Now we said that S is diagonal, so it has elements along the diagonal here that are non-zero, but all the other elements off the diagonal are 0. And in fact, in this case, you could have certain of these diagonal elements also be 0. It turns out that another nice thing about the SVD is that it sorts all these diagonal entries. These are called the singular values. So these are sorted from big to small. And so if you're going to have any zeros, they're going to appear at the end here. You may or may not have them. It just depends on the rank of this matrix. So if this matrix is rank little r, then you will have little r non-zero singular values, and the rest will be 0. Okay, so this is the standard SVD, square U and V. Okay, any questions on the standard SVD? Okay, now, if you think about this, remember that these are all zeros here. All this is 0. So that means that when that matrix multiplies by this U, it's going to kill all these elements here. So in some sense, the particular values on the right side of U will have no effect on the X matrix because they get zeroed out by all these zeros in this matrix. And furthermore, actually, if you look at this, all of these are also zeros over here. And that means that these elements of V are also unused. So if they're not used, you might say, well, why should we compute them? And that is exactly what the economy SVD does. It doesn't compute any of those values that are not directly used to construct X. Okay, so the economy SVD for the same matrix would look something like this. So here we call this U sub R, S sub R, V sub RT. I'll put a little dashed line here. Here. Okay, so essentially this U sub R is exactly this matrix here. This V sub R transpose is this matrix here. And this S sub R is this little diagonal matrix up here. So all the other things are just not computed because they're not directly relevant. So the key thing to remember here is that this SR is square, no matter what. So whereas here this matched the size of this, now this is square. And in fact, its rank is going to be the same rank as X. This is because this S has no 0 values. It has only positive entries. Okay, so those are the two versions of the SVD. This top one is going to be more convenient for derivations because you have this nice orthogonality property you can use. This bottom one is more convenient for computation because you have to compute less things. Okay, so this is the SVD. Any questions here? Okay, so let's see why we're using this. So remember that we, for PCA, talked about computing this eigendecomposition, Q. And so, as I said, one way to do it is to construct this matrix explicitly and then give it to your eigensolver and have it compute for you the eigenvectors and eigenvalues. And that is certainly one option. But it turns out that if you use the SVD, you never need to make Q. And here's the reason why. let's just imagine, let's look at what Q would be if I plug in the SVD of X. So from the previous page, X would be USV transpose, and then this X transpose here would be V S transpose U transpose. And because U is orthogonal, this U transpose U is identity, so you don't really have to think about it. And as a result, this really boils down to the V matrix from the SVD times this new matrix. But if you think about this matrix, this is a diagonal matrix times that same V matrix from the SVD transposed. And we know over here that the SVD gives us an orthogonal matrix for V transpose. Well, that's exactly what the eigendecomposition does when we have this positive semi-definite matrix Q. And we said this is diagonal. Well, diagonal and actually non-negative, and that is also diagonal and non-negative. So just noticing the correspondence here, the V that you get from the SVD is identical to the V that you would get from your eigendecomposition of Q. And meanwhile, the lambdas are nothing more than the singular values squared divided by n. Okay, so that's because when you take this S matrix, so let's say S had, let's assume X is tall, which is the usual case, so S looks like this, S transpose looks like this, you multiply them together, and you get something that looks like this, diagonal matrix. Okay, so that means that essentially, if we use the SVD, we never ever have to actually compute Q. We just start with the X matrix, we directly do the SVD like this, and this V gives us everything we need for PCA. In terms of the eigenvectors, if we want the eigenvalues, we'll see a use for them. We can get them from just squaring these and dividing by n to do this. Okay, so that's the shortcut, is we can use the SVD to compute PCA without ever having to compute explicitly the covariance matrix. Okay, so that's a huge savings when you have a lot of features, because this matrix is D by D. So, for example, if I'm working with images, if I have a 100 by 100 image, which is actually kind of small, the number of pixels in that image would be 10,000. And so if I'm saying that I have a database of images, those would be the rows in this. And so that would mean that Q is 10,000 by 10,000. So that's, 100 million coefficients in Q that you would have to compute, even if you wanted to do PCA with just like rank 1 or 2 or something. Well, if you do an SVD, you never have to compute this Q. You work directly with the images, and you run an algorithm, and it gives you everything you need without having to compute this giant matrix, which you probably couldn't even store in memory. Okay, so that's the utility of the SVD. Right. Okay, any questions? Okay, so in fact, maybe we don't even want to use the standard SVD. We might want to use the economy SVD because, like we said, the standard SVD itself computes a whole bunch of entries in U and V that we don't actually need. So what about using the economy SVD? So essentially, the economy SVD, it just gives us the first little r. So if r is the rank of X, then the economy SVD gives us these quantities. So it gives us the first little r columns of that orthogonal matrix V. And we are going to take, in most cases, just a few of those. So usually, for PCA, the rank of our approximation is going to be much smaller than the rank of the matrix X. So we just take the first R columns of what the economy SVD gives us, and essentially that's enough. Okay. So that's how we get our dictionary. This is how we can get our coefficients for Z, as we saw before. And that's computationally how we want to do it. Okay, any questions on that? Okay, we'll see some code in a moment. Now we might want to do something else. So we know that usually when we work with data sets, we like to standardize the features, because if we ever do things with regularization, that's one reason to do it. If we use a neural network, we want to standardize there, because if we don't, then the initializations that PyTorch gives us won't work well. So let's say that we have transformed our X features to Z features. Now that we have these shorter feature vectors, maybe we want to do something with them next. Maybe we want to do regression or classification if we also have labels to work with. So in that case, our new features, maybe we want to standardize them. Okay, so it turns out that we already have enough information to do this. We just need to extract it from our SVD. So essentially, for standardization, we want two things. Number one, we want that the sample mean of our Z's is 0, right? The average across all the I's of Zi is 0. And second, we want that for each feature J, the average squared value is 1. So together with this 0 mean, this guarantees that the variance for each Zj is 1. Okay, so in order to work with this a little easier without sums, but instead matrices, what we can do is we can rewrite this equality, this for all j, this way. Okay, so if you think about this is actually the covariance matrix now of our Z vectors. If we draw a picture, this is like Zi transpose. And then here is a diagonal on that matrix. So essentially, if I want to make this happen for j equals 1, so the j equals 1 elements would be the first ones. So essentially here I'm doing this, the average of those guys, of this Zi1 squared. This is the average. And then I'm looking at the diagonal of this matrix I get. So if I look at the off-diagonal elements, what I'll see is I'll see the correlations between the different elements in the Zi vector. Those are not useful for us right now. We just want the variances. So this diagonal just looks at the variances, the first times the first averaged, or the second times the second averaged, or the jth times the jth averaged. Okay. So the reason we're doing this is just this is a bit easier to work with than this. Oh, and then here's the equals the ones vector. So this is a vector of ones that makes sure that this happens for all j. Okay, so we have diag of this QZ is the ones vector. That's what we want. Okay, so let's take a look at, this is what we want here. We want this. We want these two things. We want this to happen and we want this to happen. Let's see what actually happens with the values that we have coming directly out of our SVD from PCA. So if I look at the sample mean of our Z bars, well, this is how I computed Zi. Here's the sample mean. I can move this mean through the V matrix to get this. And now you can see I have a sample mean of the xi's. Well, we said that the xi's were centered, so that sample mean is 0. So I have VR times 0, and I know that that gives me 0. My pencil has died. Let's see. Okay, I don't know why the pencil has died. Let me see. Is there a way? Battery's fine. Okay, it's back. Okay, sorry about that. So, okay, so we see that the z's are already zero mean, so we don't have to do anything with them. Let's take a look at this covariance matrix for the z's. So this is the definition of it. If we plug in the definition of zi with this, we end up getting this expression. So here's zi and here's zi transpose. We also moved the sum inside. And here we see, oh, okay, this is the covariance matrix Q of X. So this is another way of writing QZ. But Q, we know, has this expression. This is plugging in the economy SVD, the 1 over n. And it turns out that this matrix, this has R orthogonal columns, big R orthogonal columns. This VR has little r of those same columns. So when you do this multiplication, you end up getting a matrix that has an identity and then zeros to the right of it. So if that is what is happening here and here, what the effect of this is just to select the upper left quadrant of this matrix, in fact, the R by R upper left quadrant of this. And that is just a diagonal matrix where you have these SI squares over n. Okay, so that is what QZ is. We want these diagonal elements to all equal 1. So there's something very easy we can do. We can just take the square root of them. Well, let's see. So we can take the square root of them and multiply by sorry. Okay. Let me try to explain this better. So we have, this is what QZ is. If I imagine for each of these guys, if I divide by one of these s's, then that has the effect of dividing Q by that s squared. So in order to cancel this out, I just divide that element by s1. Meanwhile, in order to cancel the n, I multiply the element of z by root n. And then when you have root n times root n, that will cancel this. So here's a nice simple scaling of the zi's that gives you standardized zi's. So that essentially that's all you have to do to make sure your zi's are standardized, is do a little bit of scaling. And then you can work with them knowing that they're standardized. Okay. Any questions there? Okay. All right, so let's get into maybe the more fun stuff then. Let's look at an experiment with face data. So these are really kind of toy faces. This is from the labeled Faces in the Wild data set. It's kind of an old data set, so these faces are relatively small. They're 50 by 37 or 1,850 pixels. Still, you know, almost 2,000 numbers per face, so you might wonder, how many numbers does it really take to code a face? Can I do it in many fewer numbers? Okay, so this data set is built into sklearn. The full data set has 13,000 images. These images are all from news stories in the 2000s. Rather than using all 13,000 images, we are going to say there's a way of asking to get at least 70 faces per person. And by doing so, we're going to get a subset of 1,288 images. So these are labeled faces in the sense that you have the face itself, and then you have a label of whose face it is. So here are some examples. These are all political people from the 2000s. So number of classes would be how many different people faces we have, and then each face is 50 by 37. Okay, so here's how we do PCA. We first compute the mean of our X matrix, the mean of each column. So this is looking at the 0th axis. Then we subtract that mean vector from X, and now we have a shifted, mean shifted, or centered matrix X. Next step is we do the SVD. By doing full matrices equals false, we get the economy SVD. And in Python, or I guess this is NumPy, this is it's given to you as USV transpose, whereas in MATLAB, it would be given to you as USV. So you have to be aware that in NumPy, they already transpose the V matrix. So if we take a look at the shape of this V matrix, we expect, so remember, X is a tall matrix. There's, what is it, 1,850 pixels by, well, actually, yes. It's, okay, X actually is wide in this case. It's a little unusual, but. So 1,850 pixels by 1,288 faces. So we expect that if this matrix is XS is full rank, which it is, when we do X equals U S V transpose, we expect something like this. So, okay, so if this is full rank, the rank is the minimum of these two dimensions, which is 1288. So that means S is 1288 by 1288. That means U also has to be square in 1288 because it has to match the 1288 dimension, which means V transpose has to have the same shape as X. And V transpose is this shape, which is exactly what we expect. Okay, so now we've done the SVD. Let's do the standardization, or let's extract the eigenvalues. Lambda are the diagonal elements of S. Actually, if I remember correctly, I think maybe in NumPy this might even be a vector, whereas in MATLAB it would be a matrix. So I think this is just a vector. Yes, we're just squaring the elements of that vector and dividing by the number of samples. That's how we said we have to use the SVD for the eigenvalue decomposition. And then the last thing is, what is the proportion of variance as a function of R, the number of principal components that we use. So that we can do with cum sum lambda. That's just a cumulative sum, like starting with the first lambda plus first, next first plus second, then first, second, third, and so on. This is the top of the POV fraction, and then just summing all the lambdas is the bottom of the POV fraction. So now this is POV versus R. We can plot this, and we can see that 1 is, we know that 1 is the maximum it can be. So all the way here at 1288, it's exactly 1. But even if we use only, let's say, 300 or 400 principal components, we have a POV almost exactly equal to 1. So we can safely compress by at least a factor of 3 or 4 with PCA without really losing much, according to at least POV. So that's what we can conclude from this. Okay, any questions so far? Okay, let's take a look at some example faces. So, so here are two faces. This is the original full, the complete face. And here is the approximation as you use different numbers of PCA components. So if you want to code this face with one scalar value, the best single scalar value according to minimizing RSS, this is the approximation you would get. If you want to use 3 values, it's a better approximation. If you use 10, it's better, and so on. And here is like 300 is, we saw the POV is quite high. Yeah, this is almost perfectly this. Maybe not you can kind of see some visual differences, maybe some sharpness, but it's very close. If you were just trying to classify whose face it is, you might not need this much resolution. Maybe you could get away with more compression. Maybe this is enough to tell that this is George Bush. Right? Maybe that's enough. So we'll see. But this at least shows you qualitatively the effect of PCA for compressing these faces. And we see the same thing down here. Different face, same person, and you can see that once you get up to 300, it's really quite close to full. Even 100 is not bad. Okay. Any questions so far? Okay. So now let's look at the principal components themselves. Okay, so remember that to do this approximation, what you're doing is you're taking the mean face, so this is the mean face over the entire data set, and then you're taking this single eigenvector, and you're scaling it by some scalar value zi. So this would have one value of zi, this would have another value of zi, and those values of zi would just scale this, which you would add to your mean. So that is how you get these two images. Now, if you want to use 2 eigencomponents, zi is a 2-dimensional quantity, so you have one coefficient multiplying this, another coefficient multiplying this, you add the mean, and then that gives you the r equals 2 approximations, and so on. So it's interesting to look at what these eigenfaces or eigenvectors are. What are they coding for us? So one thing that we see in a lot of cases is it has to do with lighting. Essentially, some of these faces are lit from the left, other faces are lit, from some other direction in terms of where the shadows are. And so like what this does is this eigencomponent, whether it's positive or negative, would put brightness on the right side of the face, or if it's negative, would put brightness on the left. So that helps you, adjust the left to right brightness. This one is sort of the up and down brightness. If there's brightness from the bottom, you get brightness down here, and maybe that's what this is doing for us. Some of them, here are maybe more to do with particular shapes in the face, and so on, but a lot of this is about lighting. Okay. So anyway, I think these are pretty interesting to look at. These are basically the dictionary elements that say, how should you represent a face with just a linear combination of 6 things? Well, if you want to minimize RSS, these are the best 6 things to scale and combine to approximate the face. Okay. Any questions on this? Okay. All right, so now for this data set, we do have labels. We know the ground truth data of whose face is whose. So we can see if we can classify the faces. So what we'll do is, as usual, we'll split into training and test partitions. We'll use 3/4 for training, 1/4 for test. And so this is all the PCA processing that we did, but now just specifically on the training. This gives us our eigenvalue decomposition. And here we're constructing, we're compressing the features to get our training Z's. And here we are doing the standardization in order to, just to standardize those training Zs. So now we have everything standardized. We can train an SVM classifier. As we know with SVMs, this is a radial basis function kernel. We have two parameters to tune. Both are super important. They both need to be tuned jointly. We have the regularization C, the kernel with gamma. So we can do all this in 3 lines of sklearn. We set up a parameter grid, logarithmically spaced for C, logarithmically spaced for lambda over a couple orders of magnitude. We do grid search CV. We give it SVC with our RBF kernel, parameter grid, 5-fold cross-validation. And then we just do fit. We give it our training data, training labels, and it comes up with, its design. And if we do cross-validation accuracy, we're finding, and let's see, okay, we're doing this with 100. 100, so we're using, this quality of face here. And we find that with that quality of face, we can get 85% cross-validation accuracy. If we look at the test data, we get 83%, so that's pretty close to what we would expect. So not bad with just using 100 coefficients instead of the full 1,288. As we know, the SVC is more expensive, as the dimensionality increases. So not even sure if we could have run it with the full data, without PCA. It'd be interesting to know, but I didn't do that. So that's just an example of using PCA to compress features and then downstream do something else with them like classification. Okay, any examples? Or sorry, any questions? Okay, so it turns out that this compressing the features before classification is a bit dangerous because it could really mess you up. And so I think it worked fine in this example, but it doesn't always work fine, and I'll show you a visual toy example of where it falls apart. So imagine that I have a 2-dimensional data set, binary. So I have my samples with label 1 are here. My samples with label 2 are here. And so if I want to design a classifier, where would that boundary be? Where would I put my classification boundary?
Yeah,
just right here, right? Yeah. And this is a linearly separable data set. So with SVC or logistic regression, I could classify this perfectly, no problem, if I stay in 2 dimensions. Now let's instead say I want to be clever. I want to use PCA to compress down to 1 dimension. So looking at this scatter plot, where would the subspace for PCA be? What would it choose for PCA subspace? So remember, you're looking for the line that is so that the projections onto that line are as short as possible. And that line has to go through the origin to be a valid subspace. It has to go through the origin. So it's just a matter of how is it tilted. So where am I going to put? Yeah.
It would be perpendicular to the classifier.
Here?
Yeah.
Okay, so if we put it here, then notice that the errors can be quite large, right? And squared error means big things are magnified even more.
Would it be on the origin that's coming out of the screen?
No, this is just 2-dimensional data. So this is 2-dimensional data, so the only compression we can do is onto 1 dimension.
Yeah.
So it has to be here, right? Because here, these errors, it's shortest this way. If I turn it this way, they're longer. And if I turn it some other way, they're, yeah. So it turns out the PCA we'll want to put the subspace here. And then all these points will be approximated along that subspace. And look what happens, the 1s and the 2s, they all collapse onto that single line, and you can no longer tell them apart. It's no longer linearly separable. Kind of looks like this. Everything's mixed together. So this is an example of what can go wrong when you apply PCA, because PCA's goal is to sort of minimize the energy of the approximation error, whereas classification's goal is totally different. It's to, push apart these two classes. So they have completely conflicting goals in this case, and if you do PCA before classification, it will ruin everything. So this doesn't necessarily always happen as catastrophically as this, but it shows you that their objectives are really not aligned. And so you don't expect that PCA is necessarily going to help you if your end goal is to do classification. It may help you in the sense of reducing your complexity of training your classifier or something like that, but it's not expected to help your performance. Okay, so any questions on that? Okay, now, you might ask, well, okay, is there like some other dimensionality reduction technique that is sort of good for classification, that makes sense for classification? And the answer is yes. There is a classical technique called linear discriminant analysis, which, again, wants to project this data down to one line in this case, but it's going to choose the line in a different way. It's not going to use RSS, and it's going to explicitly use classification as sort of the end goal. And that technique would project, what would you guess that technique would choose as its subspace? What line would it choose? What subspace would be perfect for classification? Yeah, so this one, this one, right? Because then all the 1s would be here, all the 2s would be here. So now I have a one-dimensional data set that is still linearly separable. And that's what LDA will give you, because it's designed with that in mind, whereas PCA is designed with RSS in mind, more like a regression type metric. Okay, so that's just, we're not going to talk about LDA at all more than this, just to know it's out there. It's a classical method, but it's sort of the one of the fixes to this problem. Okay, any other questions? All right, so we got one more topic, which is visualization. So one of the ways that you can use PCA, or really any dimensionality reduction technique, is if you have a high dimensional data set and you want to visualize it, you just can't, because it's just these high dimensional features. Like, so, I mean, you can visualize, like we're talking MNIST, you can visualize each MNIST image on its own, but you can't visualize the whole data set together and say things about the data set. So if, however, you use PCA to go from D dimensions down to 2, now you can make a scatter plot that shows you your entire data set in one picture. So this is just one example where you start with 3-dimensional data, where it's a little bit hard to see what's going on because we're viewing this on a 2-dimensional screen. But there's these pluses are in 3 dimensions, those green things in 3 dimensions. It's kind of hard to see what's going on. If you use PCA to come up with the best 2-dimensional approximation, then it puts everything on this plane, and now we can view the plane, and now we can say, oh, okay, there's the structure of my data. The red pluses are here, and so on and so on. So as we go from higher dimensions down to 2, we can just visualize stuff. Okay. So let's look at a more interesting example. Let's look at MNIST. MNIST, I'm trying to remember how big the images are. It's like 784 pixels, I think, is the number. And we're compressing them down to 2. So this is the PCA's summary of MNIST. This is the scatter plot of all the MNIST samples, and they're color-coded. So you can see that all the 0 labeled MNIST samples are over here. The 1 labeled samples are the orange ones over here. the 2s are the green ones over here, and so on. So it's sort of interesting what PCA did with this data set. You can see some clustering of the different classes. You know, yes, the zeros are more or less together, the ones are more or less together. However, you can see there's a lot of overlap. So PCA was, you know, not really entirely successful here in terms of like telling us whether it's possible to really separate them or not. We just don't know. They seem to be pretty overlapped. Still, it's also interesting to look at how PCA came up with this representation. So if you view the eigenvectors that were learned by PCA, this is the principal eigenvector, the most important one. And this is plotted using, I believe, blue is positive, gray is 0, and 1 is negative. Okay, so this is one 784 dimensional vector. And so when we think about, you know, the role of this, it's as you go from left to right. So this value is the z value that multiplies this. So as you go to the right and you multiply this by a positive number, that's where the zeros live. Because when you multiply this by a positive number, you get you know, a big positive structure here. And on the other hand, if you multiply this by a negative number, then this one becomes positive, and that matches the ones. So here you can kind of see there's this overall 0 versus 1 kind of axis here, left to right, all encoded in this single eigenvector, the most important one for this data set. The second most important eigenvector is this one. This has a more interesting shape. You have some positive, some negative, and so on. And that tells you how you can distinguish between numbers like 9s and 2s. So you can kind of see like certain parts of a 9 here. Maybe if I combine those blue things with some of these, maybe I can create a 9, like I would have up here. On the other hand, if I have a 2, maybe I just want the top and the bottom without this part here. So that's sort of how you can, to a rough approximation, you know, get these different digits. Now, of course, you're quite limited with what you can do with a scale and a shift of those two vectors. So you can't really fully distinguish all the digits, and that's why we see this overlap. But it is instructive, I think, to see what PCA comes up with to represent all these MNIST samples. Any questions with that? Okay. And the very last thing is, so if you are interested in doing this, PCA is really, you know, it's an ancient technique. It's not really what you would want to use. However, people have developed sophisticated modern techniques for data visualization for reducing high dimensions down to 2. And probably the two most famous ones right now are TSNE and UMAP. So I won't really talk about how they're designed, but I'll just show you how they work on MNIST. So here's, again, PCA. In making this plot, whoever made this plot used much smaller dots, so you can kind of, it looks a little different than the last plot, but it's really essentially the same. You can see a lot of overlap between the different classes. But if you use TSNE, what's amazing is TSNE is able to almost perfectly separate the different classes. Maybe not perfectly. I think maybe there's, you know, some samples here that come from, I don't know if this is blue or what, but you can see it's doing a much better job than PCA is. Now, I want to emphasize TSNE was not given any labels. It was just given feature vectors, and it came up with this reduction to 2 dimensions. And in order to make these plots later, people incorporated the labels to color it, but you know, TSNE did not know about any labels. So it's pretty impressive that it was able to more or less figure out the structure of MNIST without knowing any of the labels. And then UMAP is similar, but maybe even better. It has even more of a clean separation and bigger distance between the these different clusters. So in terms of a tool, like if you are given a data set you've never seen before, you don't know maybe whether it's even possible to classify this data set, as a first step, you could just run tsne or UMAP on it and see if those techniques can just sort of cluster things roughly. And if they can do it, then that suggests, okay, it can be done. I can train a classifier to do this too, given labels. These guys didn't even have labels. They just from the features alone figured out that there's really these different classes of features. So it can be just sort of a data exploration thing that can be useful in some projects. Okay, so that's all I have for this unit. Are there any last questions? Okay, so we just got one more unit then that we'll cover next week, and that will be on clustering, basically trying to sort of do this task more explicitly in arbitrary numbers of dimensions. And we'll also talk about text processing and talk about how you make features from documents and play with some of those ideas. So that's it for today. Hope you guys have a great weekend. See you guys on Monday.